Have you ever worked on like a really complex puzzle and you hit that point where just knowing what the pieces are isn't enough? You need to know how they fit together, how they connect, maybe even like how to subtly rearrange them to get the outcome you're after.
It's a great analogy
Hmm.
because that's exactly the world we're stepping into today. The intricate and often hidden world of maintaining access to a system and building the sophisticated tools to do it.
So we're talking about red teaming tools and techniques, and there's a ton of information out there. It can be overwhelming, to be honest.
Absolutely. And that's why we're here. Think of this as your accelerated masterclass in Red Team Essentials. We've gone through a mountain of material to extract the core insights. No fluff, just the good stuff.
Love it. Efficient and targeted. So what's on the agenda for this deep dive?
First up, we're tackling persistent strategies, when to use them, when to avoid them, and the most effective methods for establishing that foothold. Then we'll shift gears and delve into the art of tool development, because let's face it, building effective offensive security tools is no walk in the park.
Definitely not a point-and-click adventure.
Right. After that, we'll dissect some absolutely crucial Windows internals concepts, the foundation upon which all these tools and techniques are built. And finally, we'll wrap things up with the world of evasion, how to stay under the radar and avoid those pesky defenders.
It's like getting a cheat sheet for understanding these really complex areas. Sounds like a plan.
Oh.
Okay, let's jump right in. And the first thing that comes to mind when you talk about red teaming is persistence, right? You get in, you set up shop, you stay in. Seems pretty straightforward. But is it always the right move?
That's the fascinating thing about persistence. It's not just a technical question, it's a strategic one. A skilled red team operator doesn't just automatically plant a flag. There's a constant risk-reward calculation happening.
So it's not just can you stay in, but should you stay in, given the bigger picture of the operation.
Exactly. And that risk assessment is heavily influenced by the target, the objectives, and the overall tolerance for getting caught. You have to ask yourself, is maintaining a persistent presence on this target absolutely essential to achieving the goals?
So it's weighing the value of that persistent access against the potential cost of getting caught. What are some of the risks that come with persistence?
Well, if you really break it down, establishing persistence often means deploying more tools, more components of your toolkit. And that inherently increases the risk of detection, right? You're expanding your footprint, and you might even expose that precious implant you've worked so hard to develop.
It's like choosing to put all your eggs in one basket. If that basket gets compromised, you lose everything.
Exactly. And sometimes the smarter move is to achieve your immediate objectives and then get out cleanly, leaving as little trace as possible. But let's say you've weighed the risks and decided persistence is essential. The next question becomes, what's the best way to achieve that?
And I'm guessing there's no one-size-fits-all answer. It's all about choosing the right tool for the job, based on the specific circumstances.
Absolutely. There's a whole spectrum of persistence techniques, from the ridiculously simple to the incredibly sophisticated. Your choice depends on the target environment, the level of access you have, and what you ultimately want to achieve.
Right, and one method that keeps popping up is the run registry key. It sounds almost too basic to still be effective.
I know, right? You'd think in today's sophisticated world it would be obsolete. But here's the thing. Despite its simplicity, the run key remains surprisingly effective. We even see advanced persistent threats, or APTs, utilizing it.
So it's still in the playbook, even for the big players. Why do you think that is?
Well, one theory is that it simply gets lost in the noise. Security teams are bombarded with so many potential indicators, they can't possibly investigate everything. A simple registry key modification might slip under the radar.
It's like hiding in plain sight. Now, speaking of registry keys, there's also the technique of AppInit DLLs. That sounds a bit more involved.
It is a bit more complex. Essentially, it leverages the way Windows loads certain DLLs into processes. You see, the vast majority of graphical applications rely on a core DLL called user32.dll.
Okay, I think I'm following. So, by manipulating specific registry keys that control how user32.dll is loaded, you can force applications to load your malicious DLL as well.
Exactly. You essentially create a list of DLLs that should be loaded alongside user32.dll. And when a user launches an application, like their web browser or even just File Explorer, your malicious DLL gets loaded along with it.
So every time an application starts, your code gets a chance to run. That's pretty powerful. But it also seems like it could be pretty disruptive if not done carefully.
Right. That's why it's important to understand the potential impact. A poorly implemented AppInit DLL can cause system instability or even crashes.
Right, you don't want to be too obvious. Now, another concept that keeps coming up is dropping to disk, which in today's security environment sounds inherently risky.
It is. Think about it. If your implant or tool can live entirely in memory, you make it incredibly difficult to detect. But the moment you write something to disk, you create a physical artifact that can be analyzed.
So you're giving the defenders something tangible to find.
Right, and modern EDRs, endpoint detection and response systems, they're constantly scanning for suspicious files, and they're getting smarter all the time. They don't just rely on signatures anymore. They analyze behavior. They look for anomalies.
So even if you hide your file really well, if it starts doing shady things, it's going to get flagged. So if you absolutely have to drop to disk, what are some strategies for minimizing that risk?
It's all about blending in. Avoid obvious locations like the root of the C drive or the user's downloads folder. Think about places where legitimate files tend to accumulate.
So like deep within the app data folder, or maybe even buried within the user's documents folder if they're the type to have a really messy desktop?
Exactly. You want to make your file look like it belongs there. And there are even more subtle tactics. For example, try not to be the first or last file in a folder alphabetically. It just makes you stand out visually.
Interesting. So it's about making your file as inconspicuous as possible. But even if you find the perfect hiding spot, there's still that moment when the file is being written to disk when it's vulnerable to detection.
That's true. And that brings up another critical question. What exactly are you dropping to disk? Is it the full implant with all its bells and whistles? Or is it a smaller, more lightweight component that just establishes a connection and downloads the rest later?
So you're saying it's smarter to stage your deployment. Keep the initial footprint as small as possible.
Precisely. You don't want to reveal your full hand right away if you can avoid it. Now, in contrast to dropping to disk, we have in-memory execution. This is often referred to as fileless malware, and it's considered much stealthier.
Because there's literally nothing for traditional antivirus to scan, right?
Right. The code never touches the hard drive. It all happens in the computer's memory. Think of techniques like reflected DLL injection, where you load a DLL directly into a process's memory, or exports like Eternal Blue, which can deliver their payload directly into kernel memory over the network.
So it's like a ghost in the machine, very difficult to detect using traditional methods. Okay, we've talked about persistence, the various strategies, the risks and rewards. Let's move on to the next big topic, developing the tools that make all of this possible.
And right off the bat, our sources emphasize that developing effective offensive security tools is anything but easy.
I can imagine. What are some of the key challenges?
Well, first and foremost, you need solid coding skills. Writing clean, efficient code is crucial. But it's not just about functionality, it's about reliability. Your tools absolutely cannot crash the target system. That's a surefire way to get caught.
Right, you don't want to be that noisy intruder that trips the alarm. So stability and predictability are key. What else is important?
Testing. Rigorous, relentless testing. It's not enough to just write the code and assume it works. You need to actively try to break your own tools, to find those edge cases, those unexpected scenarios that might cause them to fail.
So it's like putting your tools through a gauntlet of challenges to make sure they can handle anything you throw at them.
Exactly. Now, beyond the coding itself, you need a deep understanding of the target operating system, in this case, Windows.
That makes sense. You need to know how the system works, how it's structured, its weaknesses, its quirks.
Absolutely. You need to be intimately familiar with the Windows APIs, the system calls, the kernel structures. Without that foundational knowledge, you're just shooting in the dark.
So it's not just about being a good coder. It's about understanding the battlefield where your code will be deployed.
That's a great way to put it. Now, on a more positive note, there's also a huge element of creativity in this field.
Really? In what way?
Well, the security landscape is constantly evolving. New defenses are emerging all the time. So to stay ahead of the curve, you need to be innovative. You need to come up with new techniques, new approaches that haven't been seen before.
So it's like an arms race. You're constantly trying to outsmart the defenders.
Exactly. And that brings up another important point, the value of sharing knowledge within the community.
Oh, absolutely. I've seen that firsthand in the security world. People are incredibly generous with their knowledge and their time.
It's essential for the advancement of the field as a whole. By sharing our techniques, our code, our research, we all benefit.
But there's also a caveat, right? Intellectual property.
A very important point. Before you publish any offensive security tools, you need to carefully review the intellectual property terms of your employment. You don't want to accidentally release something that belongs to your company.
Definitely sound advice. Now, another point that was made is the value of knowing multiple programming languages. Why is that so beneficial in this context?
Imagine this. You've developed a fantastic implant. It's stealthy, it's effective, but it's written in a very specific language and compiled with a specific compiler. This creates a unique fingerprint, a signature that defenders can potentially detect.
Okay, I'm seeing where you're going with this. So if you can re-implement the same functionality using a different language and a different compiler, you might be able to change that fingerprint.
Exactly. Even if the underlying logic is the same, the compiled output might look completely different to signature-based detection systems. So it's another layer of obfuscation, another way to make your tools more difficult to detect.
It's all about staying one step ahead. Okay, let's shift gears now and talk about some of those foundational Windows internals concepts. And the first one that always comes up is the portable executable, or PE format.
The PE format is the bedrock of Windows executables and DLLs. It's the blueprint that the operating system uses to load and execute these files.
So if you want to understand how Windows programs work at a low level, you need to understand the PE format. What are some of the key elements to be aware of?
Well, there's the magic value, which is just a couple of bytes at the beginning of the file that identify it as a PE file. Think of like a file signature.
So it's like Windows saying, okay, I recognize this file type, I know how to handle it.
Right. Then there's the address of entry point, which tells the operating system where to begin executing the code.
It's like the starting line for the program,
Precisely. And then we have the export directory.
which is essentially a table of all the functions that the executable or DLL makes available to other programs, right?
Correct. When a program wants to use a function from another DLL, it consults the export directory to find the address of that function in memory.
So it's like a directory of services that the DLL provides. Now, our sources also mention Windows data types. That might seem a bit basic, but I'm sure there's a reason it's highlighted.
It's all about portability and consistency. You see, different computer architectures use different sizes for basic data types, like integers and pointers.
Okay, that could definitely cause problems if you're not careful.
Absolutely. So Windows defines its own set of data types with specific sizes that are guaranteed to be the same across all versions of Windows.
So it ensures that your code will behave predictably no matter what kind of system it's running on.
Exactly. And then there are handle data types. Handles are everywhere in Windows programming.
I see them all the time. They're usually prefixed with an H, right?
Right. A handle is essentially a reference to a system resource. It could be a file, a process, a thread, a registry key, you name it.
So instead of directly manipulating these resources, you use handles to interact with them.
Correct. And that provides a level of abstraction and security. The operating system manages the actual resources, and you just use handles to request operations.
It's like a ticket system.
Yeah.
You get a ticket that represents your access to a resource, but the system is still in control.
Okay, and then there are these annotations like in and out that you see in function definitions.
Oh, those are incredibly helpful for understanding how a function is supposed to be used.
I've seen them, but I'll admit I haven't always paid close attention to them. It's worth taking the time to understand them. Annotations like in tell you that a parameter is an input to the function. Out means the parameter is an output where the function will write data.
So it clarifies the direction of data flow.
Exactly. They help you write better, more understandable code.
Speaking of functions, there's one that's mentioned quite a bit, create process.
Create process is the fundamental API for launching new processes in Windows. It's a complex function with a lot of parameters, but it's essential for understanding how processes are created and managed.
So if you're writing any kind of security tool that needs to launch other programs, you need to know how to use create process effectively.
Absolutely. It gives you a lot of control over the new process, like its security attributes, environment variables, and even whether it should inherit handles from the parent process.
That level of control is important, especially in a security context. Now, related to processes, we also have Windows objects.
These are the fundamental building blocks of the operating system. Processes, threads, files, registry keys, they're all represented as objects.
And we interact with these objects using handles, as we discussed earlier.
Right. Handles provide a consistent way to access and manipulate these diverse system resources.
Okay. And one last API that was mentioned is format message. What's that one all about?
Format message is incredibly useful for retrieving and formatting error messages from the system. You know how sometimes you get those cryptic error codes?
Oh, yeah, all the time.
Well, format message can translate those codes into human-readable messages, which can be much more helpful for debugging.
So it's like having a built-in translator for system errors. That's handy. Now, we've talked a lot about processes, but let's not forget about threads.
Ah, threads, the workhorses of a process.
Okay, give me the basics. What exactly is a thread?
A thread is essentially a unit of execution within a process. Every process has at least one thread, called the main thread, which is where the program starts running. But a process can have multiple threads, all executing concurrently.
So it's like having multiple workers within a factory, all working on different tasks at the same time.
That's a great analogy. And there are specific APIs for creating and managing threads, like create thread and create a rote thread.
And what's the difference between those two?
Create thread creates a new thread within the same process. Create remote thread, on the other hand, lets you create a thread in a different process, which is a key technique for code injection.
Ah, so you can inject your code into another running program and have it execute there. That sounds pretty stealthy.
It can be, but it also requires a deep understanding of how processes and threads work. All right, we've covered a lot of ground in terms of Windows internals. Let's move on to some more advanced techniques, specifically in the realm of evasion. And the first one that jumps out is reflective DLL injection, or RDI.
That sounds pretty intense. What's the basic idea behind RDI?
Imagine you have a DLL, a library of code that you want to execute in another process. But you don't want to write that DLL to disk, because that would make it easier to detect.
Okay, so it's about being fileless.
Exactly. With RDI, you essentially load the DLL directly into the target process's memory without ever writing it to disk.
So it's like a stealthy code delivery system. How does that actually work?
It involves several steps. You first need to allocate some memory in the target process. Then you copy the DLL's code into that memory. And then you have to perform some tricky manipulations to get the DLL to execute properly, like resolving its dependencies and setting up its import address table.
It sounds really complex.
It is, but it's a powerful technique for evading detection. Now, another technique that's often used in conjunction with RDI is direct syscalls.
Okay, let's break that down. What's a syscall?
A syscall is a way for a user mode program to request a service from the operating system kernel.
So if a program wants to read a file or create a process, it needs to make a syscall to the kernel.
Right. And normally those syscalls are made through functions in system DLLs like ntdll.dll.
But with direct the syscalls, you're bypassing those DLLs and going straight to the kernel.
Exactly. And the reason for doing that is to evade detection. You see, security products often hook those system DLL functions to monitor for suspicious activity.
So by going directly to the kernel, you're potentially avoiding those hooks. Clever.
It can be effective, but it also has its drawbacks. For example, if the security product has kernel mode components, they might be able to detect that the syscall originated from an unexpected location.
So it's a trade-off, as with everything in security. Then there's also the concept of indirect syscalls, right? How do those work?
With indirect syscalls, you're still bypassing the hooked DLL functions. But instead of going directly to the kernel, you first find a legitimate unhooked system call instruction within a system DLL.
And then you jump to that instruction to make your syscall.
Precisely. It can sometimes be more stealthy than direct syscalls because it looks more like normal program behavior.
Yeah.
But again, it's not foolproof.
It's a constant cat and mouse game. Now, another technique that was mentioned is unhooking hooks. What's the purpose of that?
As we discussed, security products often hook system functions to monitor for malicious activity. Unhooking is the process of reversing those hooks, restoring the original functionality of the hooked function.
So you're basically disarming the surveillance mechanisms that this security product has put in place.
Exactly. And there are various techniques for doing this, but they typically involve finding the hook code and replacing it with the original unhooked code.
So it's like surgically removing the monitoring implants. That leads us to meet the gates. What a great name for a set of techniques.
I know, right? Catchy and somewhat ominous. Essentially, meet the gates encompasses a few related techniques: Heaven's Gate, Hell's Gate, and Halo's Gate. They're all about bypassing security mechanisms by indirectly invoking system calls.
So they're like advanced variations on the syscall theme. What's special about each one?
Heaven's Gate focuses on transitioning from 32-bit code to 64-bit code to execute system calls in 64-bit mode. Hell's Gate involves dynamically resolving system call numbers at runtime to make your code more adaptable. And Halo's Gate tries to find a clean, unhooked system call instruction by searching near the target function.
It's like finding secret backdoors into the kernel. Then we have parent PID spoofing.
Ah, that's a fun one. You see, every process in Windows has a parent process, the process that created it. Parent PID spoofing is a way to make a process appear as if it was created by a different parent process.
So you're basically forging the process's family tree.
Exactly. It can be useful for making a malicious process look more legitimate. For example, you can make it look like your process was launched by Explorer.exe, which is a common system process.
So it's another form of camouflage. Then there's the idea of a custom Windows shell embedded within an implant. That sounds pretty powerful.
It is. Essentially, you're building a mini command line interface directly within your implant. This gives you interactive control over the compromised system without relying on the standard command prompt or PowerShell.
So you have your own covert command center inside the target machine.
Exactly. And since you're not using any of the standard system tools, it can be more difficult for defenders to detect your activity.
Smart. Now, for communication with the command and control server, our sources mention the use of WinHTTP functions,
Right. The WinHTTP API provides a set of functions for interacting with HTTP and HTTPS protocols.
which are the standard protocols for web traffic. So you're essentially blending your C2 traffic in with normal internet traffic.
That's the idea. It can be much stealthier than using custom protocols or ports.
Makes sense. And then there's the concept of serialization, which is essential for reliable network communication.
Serialization is the process of converting data structures into a format that can be transmitted over a network or stored in a file.
So it's like packaging your data for safe transport?
Exactly. And on the receiving end, you have to deserialize the data to get it back into its original form.
It's like packing and unpacking a suitcase. And finally, we have certificate pinning.
Certificate pinning is a security mechanism for ensuring that you're communicating with the legitimate server and not an imposter.
So it's about verifying the server's identity. How does that work?
Instead of just relying on the standard certificate authorities, you explicitly specify which certificates you trust. So if an attacker tries to intercept your traffic and present a fake certificate, your program will reject it.
So it's like having a personal whitelist of trusted servers. Very cool. Okay, let's move on to persistence via services. We touched on services earlier, but I think it's worth going deeper.
Definitely. Windows services are a prime target for persistence. They run in the background, often with elevated privileges, and they're designed to be long-lived.
So if you can install your own malicious service, you have a pretty reliable way to maintain access. What are the key things to know about services?
Well, every service needs a few essential components. It needs an entry point, which is the function that gets called when the service starts.
It's like the main function of a regular program.
Right. And it needs a service main function, which is where the service does its actual work. And finally, it needs a service control handler, which is responsible for responding to commands from the service control manager.
The service control manager is the system component that manages all the services, right?
Exactly. And to install a new service, you typically use the Create Service API.
Okay, and that API gives you a lot of control over the service's properties, like its name, its start type, and the account it runs under. Now, one interesting technique that was mentioned is hiding a service.
That's a subtle but effective way to make your service less visible to administrators and security tools. You do this by manipulating the service's security descriptor.
So you're basically restricting who can see and interact with the service.
Precisely. And you do this using a specialized language called SDDL, Security Descriptor Definition Language.
STDL sounds complex. What are the key things to know about it?
Well, an SDDL string is a textual representation of the security descriptor. It defines things like who has access to the object and what kind of access they have.
So by carefully crafting these STDL strings, you can make your service practically invisible to unauthorized users.
Exactly. And the API you use to apply these changes is setNameSecurityInfoA.
So it's a very precise and programmatic way to control the visibility of your service.
Okay, let's move on to some alternative persistence mechanisms. The first one that caught my eye is port monitors.
Port monitors are primarily associated with printing, but they can be abused for persistence. The idea is to install a custom port monitor DLL that gets loaded by the print spooler service.
So you're piggybacking on the print spooler to get your code to execute.
Exactly. And since the print spooler often runs with elevated privileges, your code inherits those privileges.
Sneaky. Then we have image file execution options, or IEEO.
IEO is a registry mechanism that's intended for debugging. It lets you specify a debugger that should be attached to a specific process when it starts.
Okay, I've heard of that.
But you can abuse it for persistence. Instead of specifying a debugger, you specify your malicious executable.
So whenever that target process starts, your code gets executed instead of the debugger. That's clever.
It's a classic example of using a legitimate feature for malicious purposes. And finally, we have Windows Management Instrumentation, or WMI. WMI is a powerful system management framework. I've used it for legitimate administration tasks, but I can see how it could be abused.
Oh, absolutely. WMI allows you to create event consumers that can trigger actions based on various system events.
So you could create an event consumer that launches your malicious code whenever a new user logs in or whenever a specific file is accessed.
Exactly. And since WMI often runs with high privileges, it can also be a way to elevate your privileges.
So it's a very versatile and potentially dangerous tool in the wrong hands. Well, we've covered a huge amount of ground in this deep dive. We've gone from the strategic considerations of persistence to the nitty-gritty details of Windows internals and advanced evasion techniques.
It's been a whirlwind tour, but hopefully a valuable one.
Absolutely. And if there's one takeaway I hope our listeners get from this, it's that the world of offensive security is constantly evolving.
It's a never-ending arms race between attackers and defenders. What works today might not work tomorrow.
So the key is to never stop learning, never stop experimenting, and never underestimate the creativity and ingenuity of both sides. And on that note, I think it's time to wrap things up.
Until next time.